Hi everyone. So in this video we are going to learn how to calculate the resistance for various conductors of different kind of geometrical shapes. Okay, like for example, suppose simple case we have a wire whose length is L and cross section area is A. Okay, and rho is the resistivity. Okay, so for this wire we know that the resistance R, it is equal to rho L by A. Rho L by A. This is a simple case. Okay, but suppose we have a cylinder. Okay, now the cylinder is hollow in the sense the cylinder is like this. Okay, so this is the solid part and this is the hollow part. Okay, now suppose this radius is A and the outer radius is B. Okay, this is the axis, this is the axis, and L is the length, and this material has resistivity rho. Okay, so this cylinder, see here, this is also cylindrical, but this is entirely solid part. Here, this is the hollow part. Okay, so while calculating the area, we have to avoid that hollow part. So here, the cross-section area A, it will be pi b square minus a square. Outer radius minus inner radius. So that means, and length is L. So here the resistance R, it will be rho L by pi b square minus a square. Okay, so this will be the resistance of this cylinder, hollow cylinder. Okay, means the internal part is hollow. Okay, so this radius is A, outer radius is B. So this is the resistance, effective resistance. Okay, next we will see how to calculate the resistance of a truncated cone. Truncated cone. So see, this is how a cone looks. Okay, truncated cone means this part is removed. So we have this thing. So this is a truncated cone. Okay. Now for this truncated cone, we have to find the resistance. And this is entirely solid part, solid material. So this is the axis. This radius is A. This end. So here the cross section has radius A. This cross section has radius B. And L is this length, distance between the two cross sections. Okay, so for this we have to find the resistance. These data are given. Okay, and this material have resistivity rho. Okay, so now we will consider one small disc here. So this is a disc. Okay, this is a disc. So this will be like this. So I am drawing on the board. So I am drawing it as like two parallel lines. But the disc cross section, it will be like this. It will be circular. Okay. And it is of thickness dx. Radius is r. Okay. So this is the differential element, small element. So for this small element, resistance will be how much? Resistance of small element. So see, this small element, it has, so this is the thickness. So this thickness is dx, radius is r. So this current will flow like this. So this dx will be like length of the conductor, and from this r we can calculate the cross section area. resistance general formula is R equal to rho L by A. So for this small element, what will be the resistance? Small resistance dr, it will be rho dx by pi r square. Rho dx by pi r square. Okay, so that is the radius of this disc. Now see, what is the radius of this part? A. Now as you move in this direction, the resistance, now the radius of this cross section is A, the radius of this cross section is B. Now the radius of this cross section is A, the radius of this cross section is B. So as you move from this end to this end, the radius changes from A to B, and somewhere in between these two edges, the radius becomes R. Okay, so how this R is related to A and B? So I can write R is equal to, suppose this disc is at a distance x from this end. Here, from this cross section to this point, the distance is x. Okay, so see, this radius changes from A to B when we move through a distance L. The radius changes from A to B when we move through a distance L. So what will be the increment in radius as you moved from A to B? It is B minus A. When you move from this end to this end, so when you move through a distance L, the increment in radius, it is B minus A. B minus A. This is the increase in radius when you move through a distance L. So when you move through a distance x, what will be the increase in radius? It will be B minus A by L into x. B minus A, see, B minus A, this is the increase in radius when you move through distance L. So when you move through 1 unit distance, the increase in radius will be B minus A by L, isn't it? So when you move through distance x, the increase in radius will be B minus A by L into x. So this radius has increased from which amount? From A. So this radius R will be A plus increment in radius. So that will be equal to R. So this is the value of R. Okay. So this R can be substituted over here. Correct? So we can write this dr as dr is equal to rho dx divided by pi A plus B minus A by L into x square, r square, so square of this. Okay, so this is the resistance of this small element. So if we integrate this, so there can be so many small such elements. So for each element we can find the resistance and then we can add. Okay, so instead of finding the resistance of each small element and then adding, we will integrate this. So we will integrate this from this end to this end, so that this length is L, so 0 to L. So this will give you R. So I have to integrate this from 0 to L. 0 to L. Okay, so next step is evaluation of this integral. Okay, so what we will do, we can replace this a plus b minus a by L into x as y. Okay, such that, so here a, b, these quantities are constant, only variables is y and x. So we have dy, it is equal to, this becomes 0, b minus a by L into dx. So that gives dx is equal to L dy divided by b minus a. So this dx can be replaced by this term, correct? So I can write r, or I can write this as integral rho dx is this quantity L dy by b minus a, dx is this quantity, rho we have, this is pi, and what is this? This is y, so this will be y square. Okay, now this limit is going to change. Okay, so how to find the value of this limit? See, here the value of this x was changing from 0 to L. Now x is replaced by y. So when x is equal to 0, y is equal to a, so lower limit is a. Okay, when x is equal to L, so this is L, so this L gets cancelled, a gets cancelled, so y is equal to b. So upper limit will be b. Okay, so this is now a simple calculation. So we have changed the limit. So now this is r, it is equal to rho L by pi b minus a integration dy by y square a to b. Okay, so this is y square can be taken here, so this is y power minus 2. So this on integration y power minus 2, this becomes r is equal to rho L pi b minus a, this is minus 1 by y on integration. So limit is a to b. Okay, so if I change this minus sign, the limits also changes. So this is a, this is b. Okay, so this is r is equal to rho L by pi b minus a, 1 by a minus 1 by b, correct? So this is r is equal to rho L pi b minus a divided by ab. So this b minus a gets cancelled. So we get the expression of resistance as r is equal to rho L by pi a b. So this is the expression for the resistance for this truncated cone whose one side cross section radius is a, the other side cross section radius is b. L is the length, okay, rho is the resistivity. Okay, now as you can see, if a becomes equal to b, okay, if a becomes equal to b, so that is now this cylinder, so this is a, this is also a. So in that case, this is r is equal to rho L by pi a square. So that is nothing but rho L by a cross section area. Okay, so that is the thing result we know for normal cylindrical resistance, cylindrical conductor. The resistance is like this. Okay, so I hope this derivation is clear to you. Achha, next, suppose we have again a cylinder whose inner radius, so this is the axis, this inner radius is a, okay, a is the inner radius and outer radius is b. This part is hollow, okay, But now the current is not flowing like this, the current is flowing in the radially outward direction. Okay, so if there is a radially outward flow of current, what will be the resistance? Okay, so for this diagram, let me draw this from the cross section. So this is the cylinder with outer radius B. Okay, and this inner radius A. So this part is hollow, this part is empty. Only this part is the solid part. This part is the solid part. Okay, this part is the solid part. And the current is flowing in radially outward direction. So if the current flows in the radially outward direction, how to calculate the resistance? Okay. So now what we will do, we will consider one strip of radius x. Okay, so this strip, it has thickness dx, radius x, and this cylinder is, remember, a cylinder is like this. So L is the length of the cylinder. L is the length. Okay, we are observing the cross section. The current is flowing like this. Okay, so for this strip, the current goes through this direction, so it is traveling through a length dx, isn't it? So for this small element, what will be the resistance? What will be the resistance? Can we write the resistance dr as, like if say rho is the resistivity, so dr is equal to rho length dx. Length dx, it is traveling through length dx. So what will be the total area? So total area, see, suppose this is the this cylindrical part. So area means this entire area, this area. So this circumference is twice pi x, length is L. So area will be twice pi x into L. L is the length of the cylinder. Correct? Acha. So the total resistance will obtain by integrating this expression from inner radius A to outer radius B. Correct? So if this expression is understood, then the calculation is very simple, because dx by x rho by twice pi L, dx by x integration is natural log x, limit is a to b. So this is r is equal to rho by twice pi L ln b by a. So this is the expression for the resistance. Okay. Achha. Now suppose instead of having a cylinder, hollow cylinder, suppose this is a sphere. This same diagram can be used to understand the resistance of a sphere. Suppose this is a sphere with this hollow part. So this is a sphere, outer radius is B, inner radius is A, this is the hollow part, and this is the solid part. Resistivity of the material is rho. Okay. So now what will be the resistance? So again we are going to consider a small element. Now this case, that small element, this will be a spherical shell of radius x, thickness dx. This spherical shell, the resistance dr, it will be rho, resistivity of the material, dx is the thickness, so that is equivalent to the length. So current is traveling through this length dx, because current is traveling in radially outward direction again. So this is rho dx divided by area. Resistance general formula is R equal to rho L by A. Area is the surface area of the shell, so that is 4 pi x square. X is the radius of the shell. So the resistance will be obtained by integrating this from A to B. So this is R is equal to rho by 4 pi dx by x square. Integrating this is minus 1 by x limit is a to b. So if you change this minus sign, the limits will change. So this is a, this is b. So this is r is equal to rho by 4 pi 1 by a minus 1 by b. So r is equal to rho b minus a divided by 4 pi ab. So this is the expression for the resistance of a hollow sphere, okay, where the current is flowing radially outward direction. Okay, so this is how we can calculate the resistance for various geometrical shapes. Okay.